Module 7, Section 10.5, Powers and Roots of Complex Numbers. First, let's look at powers of complex numbers. Here we want to raise our polar form number to the power of 2. So what we see here is it's been written twice, and we multiply it out using our product rule, which means we multiply our r values to get r squared, and add the angles. So we have cosine of 2 theta plus I sine of 2 theta. In the same way, when we raise it to the third, we'll get r to the third, cosine of 3 theta plus I sine of 3 theta. You should be noticing a pattern, and this is what we call de Moivre's theorem. It states that if we have a number written in polar form that's complex, and n is any real number, then when we take our number and raise it to the power of n, we have the following: r to the n times cosine of n theta plus I sine of n theta, or also written in compact form with CIS. Now let's do an example. Here we want to raise our complex number to the 8th power and express the result in rectangular form. So in order to do that, we need to convert it to trigonometric form. So we need to find our r value and we need to find our theta value. So we'll do that on our calculator. We do second apps 5, and we enter in our first value of our complex number, which is 1, or our real part, and then we enter in our imaginary part, or the coefficient of our I term. So we see that we get an r value of 2, and now we'll find theta the same way. We do second apps and use number 6, and we'll enter our real part and then our imaginary part, and we get 60 degrees. So r was 2 and theta was 60 degrees. So we'll rewrite it in our polar form, and we have 2 times the cosine of 60 degrees plus I sine of 60 degrees. And this is being raised to the 8th power, which means that we'll take our r value and raise it to the 8th power, and then we'll multiply our angle by 8. So we end up with 256 times the cosine of 480 degrees plus I sine of 480 degrees. So we want to evaluate the cosine of 480 and the sine of 480 degrees. So we'll look at our graph. And first we need to find the coterminal angle. So we'll subtract 360 degrees, and we get 120. And we see that we're then in quadrant 2. So we find our reference angle here to give us our right triangle. And that'll be 180 minus 120, or 60 degrees. And we see then when we fill out our triangle, we have the square root of 3 over 2. Here is 1/2, which is negative, and 1. So when we take the cosine of 480, or 120, we'll have our x value, or our adjacent over the hypotenuse. So we have negative 1/2 plus I times the sine of 480, which would be our y value, or opposite over hypotenuse. So we have the square root of 3 over 2. Now we'll distribute 256 to both, and when we do that, we'll see that we get a value of negative 128 plus 128i times the square root of 3. Now let's look at roots of complex numbers. For a positive integer n, the complex number a plus bi is the nth root of the complex number x plus yi if a plus bi to the nth power is equal to x plus yi. We also have this nth root theorem. If n is any positive integer, r is a positive real number, and theta is in degrees, then the non-zero complex number r cosine of theta plus I sine of theta has exactly n distinct nth roots, given by the nth root of r times the cosine of alpha plus I sine of alpha, where alpha is defined as follows: theta plus 360 degrees times k over n, or we can split it up into two fractions, where k is 0 through n minus 1. So 1 less than the root we're taking. Now this can also apply when theta is in radians. So when theta is in radians, we define alpha as theta plus 2 pi times k over n, where k is still 0 through n minus 1. In this example, we want to find the two square roots of 4i. We'll write the roots in rectangular form and check our results with a calculator. So first we want to write 4i in trigonometric form. So we have 4i. We know that this is the same as 0 plus 4i. So in this case, x is 0 and y is 4. So we want to find r and theta. So we'll do second apps 5 with 0 and 4. We get a value of r of 4. And we'll do second apps 6 with 0 and 4. And we get a value of 90 degrees. So we have 4 for r and 90 degrees. But let's convert this and change it to radians, and we'll do radians for this example. So this would be pi over 2. So our trig form, 4i, becomes 4 times the cosine of pi over 2 plus I sine of pi over 2. And what we want to do is we want to take the square root. So n in this case is 2. So we'll take the nth root of r, so we're taking the square root of 4, times the cosine of alpha plus I sine of alpha, which will be equal to 2 times, now we need to find our alpha values. Remember, alpha is theta plus, in this case we're using radians, so we have 2 pi times k over n, and k will take on the values 0 and 1, since we go up to 1 less than n. So alpha is theta, which is pi over 2, plus 2 pi times 0 over 2, and alpha is also pi over 2 plus 2 pi times 1 over 2. So when we work these out, 2 pi times 0 goes away. We have pi over 2 divided by 2, which means we're multiplying by 1/2. So we'll get pi over 4. And here we'll have pi over 2 plus 2 pi divided by 2, which will be 5 pi over 2 times 1/2, or 5 pi over 4. So we see that our two square roots are 2 times the cosine of pi over 4 plus I sine of pi over 4, and 2 times the cosine of 5 pi over 4 plus I sine of 5 pi over 4. But we want to convert these to rectangular form, so let's look at our coordinate plane. Pi over 4 is going to be in quadrant 1, and we have the square root of 2 over 2, square root of 2 over 2, and 1. So here we'll get 2, the cosine of pi over 4 will be the square root of 2 over 2, plus I sine of, plus I, and the sine of pi over 4 is the square root of 2 over 2 as well. Now when we distribute the 2 to both, you'll see that it cancels out with our denominators here, and we'll get the square root of 2 plus I square root of 2. Now let's look at 5 pi over 4. 5 pi over 4 is going to be in quadrant 3. And we see that our reference angle here is pi over 4. So we have square root of 2 over 2, square root of 2 over 2, both negative, and 1. So the cosine of 5 pi over 4 is going to be negative square root of 2 over 2, plus I times the sine, which will be negative square root of 2 over 2 as well. When we distribute our 2 here, we'll get negative square root of 2 minus I square root of 2. So now let's check on our calculator. One way to check is to type in our equations and our numbers and square them to see if we get 4i. So let's take the square root of 2 plus I, which is second decimal, times the square root of 2, and we want to square it, and we see we get 4i. And let's do the same with our negative value. So we have negative square root of 2 minus I square root of 2 squared, and we see we also get 4i. Now another way we could do this with a square roots, when you're taking the square root of 4i, you can just simply type in second square root of 4i and make sure that your mode is in a plus bi mode and hit enter, and you see that we get these decimal values. But when you take the square root of 2, notice that it's identical to our decimal values here, so it's done our positive square root for us, and to find the negative we do negative square root of 4i, and we see then we get our negative answer. Now let's find all fourth roots of negative 8 plus 8i square root of 3 and write the roots in rectangular form. So in this case, x is negative 8, y is 8 square root of 3, and we want to find r and theta. So we'll do second apps 5 of negative 8 and 8 square root of 3, and we see we get an r value of 16, and we do second apps 6 negative 8 8 square root of 3, and we get 120 degrees. So we'll leave it in degrees this time. So we see that our number negative 8 plus 8i square root of 3 becomes 16 times the cosine of 120 degrees plus I sine of 120 degrees. And what we want to do is take the fourth root, so in this case n is 4, so we'll take the fourth root of 16 times the cosine of our alpha plus I sine of our alpha, and we'll get 4 values. Now the fourth root of 16 is going to be 2, but alpha will be, remember, theta plus 360 degrees times k over n, where k is going to be 0, 1, 2, and 3. So we have alpha is going to be 120 plus 360 times 0 over 4, 120 plus 360 times 1 over 4, 120 plus 360 times 2 over 4, and 120 plus 360 times 3 over 4. So when we work these out, we'll get a value of 30 degrees, 120 degrees, 210 degrees, and 300 degrees. So we have 2, and let's use our compact form instead of writing it out for all 4. We have 2 CIS of 30 degrees, 2 CIS of 120 degrees, 2 CIS of 210 degrees, and 2 CIS of 300 degrees. Now what we want to do is convert these to rectangular form, so we need to find the cosine and sine of each of our angles here. So let's draw our coordinate plane. We see that 30 degrees is in quadrant 1. We'll have 1/2 square root of 3 over 2 and 1. 120 degrees is in quadrant 2. So when we do our reference angle, we'll get 60 degrees, which we would have square root of 3 over 2, negative 1/2, and 1. And now let's do our other angles. 210 degrees is going to be in quadrant 3. We draw our reference angle and we'll get 30 degrees. So we'll have negative 1/2, negative square root of 3 over 2, and 1. And then 300 degrees is going to be in quadrant 4. And our reference angle here is going to be 60 degrees. So I'll have negative square root of 3 over 2, positive 1/2, and 1. So now notice that we'll end up with 2. The cosine of 30 degrees is going to be square root of 3 over 2 plus I sine of 30 degrees, which is 1/2. And then we'll have 2 times the cosine of 120, which is going to be negative 1/2, plus I times the sine, which would be square root of 3 over 2. And we'll get 2 times the cosine of 210, which is going to be negative square root of 3 over 2, plus I times the sine, which would be negative 1/2. And then 2 cosine of 300, which would be 1/2, plus I times the sine, which would be negative square root of 3 over 2. Now when we work each of these out, here we'll get the square root of 3 plus I. Here we'll get negative 1 plus I square root of 3. Here we see we have negative square root of 3 minus 1, I. And here we'll have 1 minus the square root of 3, I. Or I square root of 3. Let's look at solving an equation by finding complex roots. In this example, we want to find all complex number solutions of x to the 5th minus 1, and then graph them as vectors in the complex plane. So the first step is to rewrite our equation x to the 5th minus 1 equals 0, and we'll solve it for our x to the 5th, so we'll get x to the 5th equals 1. So to find our 5 complex number solutions, we'll write 1 in polar form. So in this case, x would be 1 and y would be 0. So we'll find our r value and our theta value on our calculators we've done previously, and we'll get a value of r of 1 and a value of theta of 0 degrees. So when we rewrite it, we'll get 1 equals 1 plus 0I, which is equal to 1 times the cosine of 0 degrees plus I sine of 0 degrees. And remember, we're taking the 5th roots, so n is 5. When we take the 5th root of 1, we'll simply get 1, and then we'll have the cosine of our alpha plus I sine of our alpha. And alpha is going to be theta plus 360 degrees times k over n, where k is 0, 1, 2, 3, and 4. So we'll have that alpha equals 0 degrees plus 360 times 0 over 5, 0 plus 360 times 1 over 5, 0 plus 360 times 2 over 5, and so on. We work each of these out. we'll get 0 degrees, 72 degrees, 144 degrees, 216 degrees, and 288 degrees. So we see that our roots are 1 times the cosine of 0 degrees plus I sine of 0 degrees, 1 cosine of 72 degrees plus I sine of 72 degrees, 1 times the cosine of 144 degrees plus I sine of 144 degrees, and so on.